the actual argument that I'm hoping to see. So just like before, it's going to say something along the lines of for all natural numbers n. So there's this universally quantified statement out in front. I'm going to have this nice little predicate, which I am again going to denote by Pn, just to keep everything somewhat consistent with what I saw last time. What I'm going to have to show is that in the basis side of things, I'm going to have to show that P1 is actually true. So at level 1, what's going to happen is that if I plug 1 into the left-hand side, so it's going to be 2 up to 3 times 1 minus 1, and if you think about 3 times 1 minus 1, that's a 2. So that's just that 2 to 2, which is just a 2. And then my right-hand side is going to be, okay, plug 1 into that thing, so 1 times 3 times 1 plus 1 all over 2. That's going to be a 4 over 2, which is again a 2. So that does work. So just for consistency, I'm going to do one more stage just so you know that these terms are going to be building. Sometimes actually having these kind of slightly more bizarre looking terms throws some students off. They want to say that this is, a sum of just, 1 to 2, or they somehow add in extra terms or forget terms. So just kind of realize that the 2 level is going to be 2 terms on the left-hand side. That is, it's going to be a 2 up to 3n minus 1, which in this case is a 3 times a 2, which is 6, minus 1, which is 5. So it's a sum from 2 to whatever that thing kicks out, which in that situation is going to be a 5, and that does in fact kick out a 7. And the right-hand side on that thing is going to be a 2 times a 3 times a 2 plus a 1, and then all of that over a 2. And if you compute that out, it does in fact kick out a 7. Likewise, if I wanted to look at P3, it would be 2 plus 5 plus 8. It's the first 3 terms in this little list, and that does, again, kick out a 15. And if you plug 3 into that formula, it'll kick out a 15 as well. So officially, at least in terms of the induction, all I need to do is I need to show my basis step, but it never hurts to do a couple extra examples just to kind of get your ground set, just so you know what's going to be happening before you get into this whole world of k's and k plus 1s and all those things. It never hurts to do a bunch of these examples so you know what's happening, so that when you kind of get lost in the algebra, it's not such a scary place to be. You're like, oh, it should be doing this and this and this, and it in fact does actually do that. So when it comes to the actual induction side of things, I get to now assume my level pk, and I'm going to try to show that pk plus 1 is true. Officially, it's going to be this pk is then supposed to imply pk plus 1. This is my induction step. That pk is then going to be my inductive hypothesis, and then I'm going to try to show this new little conclusion. So level pk is now true, so I'm up at whatever random height I want. That is, I get to assume 2 plus 5 plus 8 all the way up to a 3k minus 1 is then equal to a k times 3k plus 1 all over 2. That's what I get to assume. What I want to show, or my goal, is to show that pk plus 1 is true, the next level up. So in this case, if I look at this random formula, what's going to happen is that I'm going to replace the n with a k plus 1. So the left-hand side is still going to be a 2, a 5, and an 8. And then it's going to go up to a 3k minus 1. And then there's one more term that's going to be added to this thing. In this case, the next term is going to be a 3 multiplied by k plus 1 minus 1. And then my right-hand side of that thing is going to now be k plus 1's replaced in for that n. So it's going to be a k plus 1 multiplied by a 3, k plus 1 plus 1 all over 2. I like to clean these things up just a little bit so I know what I'm going to be staring at. It's going to be a 2, a 5, an 8, all the way up to a 3k minus 1. And then plus, if I distribute the 3, I get a 3k, and then a 3 minus 1, so a plus 2. So my next term now is a 3k plus 2, rather than that horrible mess that's that. And that's supposed to be now equal to a k plus 1. And then this is going to be a 3k, distributing the 3 and then adding 1 is going to be a plus 4, all of that over 2. So my goal is to get to the blue stuff. I get to assume the red stuff. So how do I make that connection? Well, I do the exact same thing that I did last time. I start with that left-hand side of what my goal is. It's a lot of writing on these ones, but the general process is pretty quick. It's just a lot of writing these terms over and over and over again. So these first k terms are exactly the left-hand side of what I know. That is my inductive hypothesis coming into play, is that I can re-represent those first k terms with something that looks a little bit nicer. It's just a k, a 3k plus 1, all of that over a 2. And then what's going to happen is that I still have that next term. And that next term is this 3k plus 2. So my goal now is to take this kind of collection of two things added together and hope to see that that is going to emerge. So all this requires me to do is to do a little bit of algebra. And I'm going to be a little bit lax with some of the notation just because I'm about to run out of space. I have to do all the algebra in about 1.5 inches here. So what I need to do is I need to find a common denominator. So I'm going to give both of those things on the right-hand side a 2. So the top and the bottom both get a 2. So it's essentially like multiplying by a really fancy 1. The left-hand side, if I distribute the k and then combine everything, is going to give me a 3k squared plus a k. And the right-hand side is going to be a 3k times a 2, which is a 6k, and then plus a 4. And then all of that's going to be divided by a 2. So if you see those middle bits, you can actually re-represent that k plus 6k as a 7k. And now I actually have this bit that looks like a 3k squared plus a 7k plus a 4. And my goal is to factor this thing. Again, I actually know how it's going to factor, so I can use that to my advantage to say, okay, I need to have a k and I need to have a 3k, because that's the only way to make a 3k squared. And then at the end of the day, I'm going to have a 1 and a 4 or 2 2's on the backside, but I do need it to make a 7 in the middle. So what's going to happen is that I'm going to have to take the k and then multiply that by a 4 to give me 4k's, and then I got 3 more of them in the middle, so I get a plus and a plus there. So this whole thing is going to turn into a k plus 1 and then a 3k plus 4 all over a 2, which is exactly what I was supposed to see. So again, you know how it's supposed to factor, so use that to your advantage. It's not such a hard factorization when you know where you're supposed to go. Just make sure it does actually get to what you're supposed to, that you didn't get lost, you forgot a negative sign, or you lost a plus sign, or something like that. There's a lot of distributions that can actually occur, so just be really careful when it comes to working through some of those things. So if you'd like to, we can actually scoot through the actual argumentation relatively quickly. So I had my big old statement that said for each natural number n, I have blah occur. If you'd like to actually re-represent the left-hand side using summation notation, what it would be a sum from k equals 1 up to the value of n. And now my terms are going to look like a 3k minus 1. So if you want to get extra fancy with these things, you can actually represent it like that. Just be really careful with your parentheses, so your -1 is actually part of your summation and not just a random -1 that's going to be floating on afterwards. So what ends up happening is I have this big claim actually happening. I'm going to identify this nice little predicate Pn by the actual statement that I'm dealing with. My two big steps, my basis step is to show that this thing is true when n is 1, which it is in fact, plugging in 1 to the left-hand side and plugging in 1 into the right-hand side. Both end up kicking out at 2. So then I enter my world of my inductive step. So I get to assume this stuff in red is true, i.e. at level k, this is actually going to be true. So I have all of the big summation from 2 up to this 3k minus 1, so the first k terms in this little sequence. And then that thing is supposedly going to be kicking out this giant mess over on the right-hand side, which we've seen, and hopefully it does actually believe that it's going to be true. What I got to do in that case is I have to show that the level k plus 1 is actually true. So just like before, I tried to isolate this as being in this blue font, and then the inductive hypothesis is in red font. So my goal is to get blue. I want to show this is true. I do not get to assume this. I have to show this. I do get to assume this boxed in part. So there's a subtle change of notation there, but it's a substantial one. I get to assume the red, and I have to show the blue stuff. So the way that we do that is we take the left-hand side of the blue stuff, which is really just the left-hand side of the stuff that I know, but just with a little bit more. And then I do all of the algebra magic that we just saw on the last side, and I got to where I'm supposed to get to, so yay, there is much rejoicing. And then if you want to, you can finish this off by saying, hey, by the principle of mathematical induction, everything is great, and this formula is in fact going to be true. So it is the exact same block of text that I had last time. The only thing that changed is the algebra stuff in the middle, as well as what my inductive hypothesis was, as well as my goal. But everything else was the exact same. So hopefully you can start to kind of realize that as you go through these things, they take a little bit of algebra magic in the middle, but structurally they are identical, which is kind of the nice thing, as well as the kind of annoying thing about some of these early induction arguments, is that they're kind of formulaic as well as kind of cookbooky or Mad Libsy, that you're just kind of plopping in various pieces. So I really want you to step back and make sure you know what all those pieces are actually doing. You get on the ladder, and then you go from rung to rung to rung, so you can actually climb the ladder as high as you'd ever want to.